Yeah, okay, so here's where we're picking up from last time. We're starting section 2.6. I want to remind y'all first off of a few things that we know about partial derivatives. So here we go, partial derivative. There's our notation for it. On the one hand, it's the slope of a graph. Right? Specifically now, it's the slope of the graph when you're looking in the direction of that standard basis vector. Keep in mind, partial derivatives are all about standard basis vectors. Second interpretation, it's a multiplicative factor. It's how much you multiply by input change to get output change, be that a discrete change or an instantaneous rate of change. Let's not get lost in the details there. It's a multiplicative factor. You multiply by input change to get output change. Right. Again, when you're moving in the direction of that standard basis vector, partial derivatives are only for standard basis vectors. Okay, now here's a couple of weird ones that you might not recognize. We've not really quite written these down before. I'll start off with this one here. This formula seems like a weird way to write it, but if you think about it, the gradient, right? What is the gradient? It's just all the partial derivatives, and if you dot it with that same standard basis vector, mostly zeros, right? With a 1 in a single position, and so this dot product will just give you that partial derivative, right? So it's another take on a partial derivative is that it can be computed by this formula. Whether this is useful or not, okay, well, that remains to be seen, right? But nevertheless, this is another point of view on partial derivatives. The last one here is this right here. And again, this looks strange. I'm going to zoom so I can do some hand waving here. We can get this thing to behave. There we go. So keep in mind the partial derivative says, okay, I'm at the point A. I'm going to be moving just in the direction of the xi variable. Only in the direction of xi. Said differently, only in the direction that ei points. Right? Another way to say it. So I'm at A, I'm moving in the direction of ei, and I want to know how fast f is changing. Now let's look at this expression right here. And starting with the expression on the inside here, the little parametric curve, which you'll notice, when t is equal to 0, this is at A, and moving in the direction given by ei. And apparently, as we do this, it says we're keeping track of how fast f is changing. So, in fact, both of these expressions right here say exactly the same thing. They both say we're at A, moving in the ei direction, and keeping track of how fast f is changing. So that's, I think, a sort of an easy point of satisfaction that this also is equal to the partial derivative. And if you don't like that point of view, well, then you can just, literally write this down as a limit, and you'll find that you get exactly the partial derivative. Okay. All right. So what? We have these various different points of view on the partial derivative. I want to take a pause here and kind of step back and think about how we're doing. I mean, what does all this mean, right? And I'm going to revert to one of my standard examples. Let's think about the temperature in this room, right? So there's our domain is the room itself, 3 dimensions, and at any given spot, like at this point right here in the air, there is a temperature. And over there in the corner, there is a temperature. And back there in that corner, there's a different temperature. Right? So temperature is a function of location in this room. And notice, no coordinates. Right? Points in this room are just points. They're just geometric objects. Temperature is a function of location. Coordinates are a figment of our imagination that we make up for sort of convenient algebraic purposes. They're not really what we're talking about. Okay, so now with that in mind, how do we set up coordinates? And the answer is, however you want to. Go crazy, knock yourself out, whatever. Set up any coordinate system you like. Right? Now, a reasonable choice would be to notice the walls and the floor and the ceiling and pick a coordinate system kind of like this. right? Use unit vectors pointing in these orthogonal directions seems convenient. And once you've made that choice, once you've set up your coordinate system, okay, well, now we have standard basis vectors. And all of a sudden, that direction is an important, significant direction. And likewise that way, and likewise that way. And that direction's nothing. Right? Is everybody kind of with me so far, right? But the big important idea I'm trying to get across is when I say that those directions are important, but that direction's not, it's because I arbitrarily set this up as my trio of standard basis vectors. It was an arbitrary choice. I pulled it basically out of thin air, no pun intended. I didn't have to. I made it up. I am perfectly within my rights to pick this as my axis system, and thus these as my standard basis vectors. Right? Whatever. And if I do, now let's think about what the result would be if I were to take this right here as my standard basis vectors. Now notice that direction that previously was nothing of particular significance. Now that is a standard basis vector. All right, so the punchline to all of this is that while partial derivatives are useful and connect to a lot of things and can be computed with various formulas, blah, 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 very nice, this restriction that they only apply to standard basis vectors is kind of an illusion based on the coordinate system that you chose. It's not really an absolute. So I would propose, I think this is reasonable, that because any unit vector could be a standard basis vector with respect to some appropriate choice of coordinates, something along these lines ought to make sense for any unit vector, not just standard basis vectors. And in fact, this is exactly how it turns out. It is true that for any for any unit vector, doesn't matter, take your pick, any unit vector, in the same way that these four, color problem, these four things here are all equal to each other and all represented by a single expression. Likewise for any other unit vector. Any other unit vector, you can write down this expression. You can compute this dot product. You can talk about the slope of the graph in that direction. You can talk about the multiplicative factor as you move in that direction. These are all four equal to each other, and for all the same reasons that it works for standard basis vectors. Because, again, any unit vector could have been a standard basis vector. So the big idea here then is, while previously, when we were restricting ourselves to standard basis vectors with respect to the coordinate system we picked, and these interpretations only applied to standard basis vectors, now we have this whole new interpretation, right? These things are all together for any unit vector. We can't call these partial derivatives because we did in fact pick a coordinate system, and we do want to look, coordinates are nice. I do like coordinates, right? Even if they are arbitrary and not absolutes. They're very handy. So we don't want to abandon our coordinate system, so we can't call these partial derivatives. We make up a new name instead. We call them directional derivatives. It's just terminology. It's a reasonable choice, arguably. So this is our big idea for this section, directional derivatives. And again, you can think about directional derivatives in any of several senses. A directional derivative, this is the notation. This is the definition. This is a handy formula for computing them. And these are the interpretations. It is a slope of a graph. It is a multiplicative factor. So just by kind of stepping back and reminding ourselves that coordinate systems arbitrarily chosen, we've got a tremendously powerful new concept that we just stole for free from our existing idea of partial derivatives. And this is how I encourage you to think about directional derivatives in general. Directional derivatives, I encourage you to think of them as being basically partial derivatives. They literally are partial derivatives if you're just thinking in a different coordinate system. Okay. Now there is one other thing I want to point out, and that is if you think about this idea that a partial derivative and therefore a directional derivative is a multiplicative factor. Let's talk about notation. Keep in mind when I say multiplicative factor, I mean it's what you multiply by input changes, discrete or rates, to get output changes, discrete or rates. Now, what do you think we should call the thing that you multiply by ds to get df? And related question, what do you think we ought to call the thing that you multiply by ds dt to get df dt? And the obvious answer in both cases is df ds. This is a lovely choice of notation. This says that, look, as you're moving around in your domain, the directional derivative gives you rate of change of the function with respect to distance traveled in that direction. Not rate of change with respect to time. The directional derivative is rate of change with respect to distance traveled. So per unit distance that you move in your given direction, how much does the function change? How are we doing on this? All right. Okay. So, a lot of new information here. Do keep in mind, unit vectors, right? This has to be a unit vector, and with that, directional derivative denoted like so, defined like so, computed like so, and interpreted like so. Let's see an example. We have a function here. We apparently are looking at the graph of this function, and I want to know what is the slope of the graph of that function. Now, of course, there's a bunch of different directions in which you could be looking. Do we mean slope in the direction of one of the axes, like partial derivatives used to tell us? No, in this case, we are at a certain point and looking in the direction given by that vector right there, not parallel to an axis. How are we going to understand the slope of the graph in that direction? And this has a very immediate first part of the answer. Slope of the graph is one of our primary interpretations of directional derivative. Right, our newly defined, our new ripoff of the idea of a partial derivative. Stealing the interpretation of partial derivative 2, right? Just applied in a different direction. Okay, cool. So we're going to use our handy-dandy formula to compute directional derivatives, dot product with the gradient. And it's all downhill from here. Let's see here, the gradient itself, of course, you're going to compute the gradient by taking the appropriate partials. You plug in the point in question, and that tells you the specific gradient that you need to use. One little slightly tricky bit, a lot of students forget that, again, very carefully, looking back here at our definition of a directional derivative, do note, very importantly, this vector that indicates the direction has to be a unit vector. Keep in mind, the whole idea here is that I'm just going to take what used to be my standard basis vectors and just make a different choice for standard basis vectors. Of course, standard basis vectors need to be unit vectors. So don't forget that you have to use a unit vector. So if I want to know the unit vector pointing in the direction of that vector right there, well, I have to divide by its own magnitude. Does that make sense? Right. By the way, there's another way to think about this. I think this is a useful point of view. Very often, in fact, we think of unit vectors as being a mathematical way to represent a direction. And I think it kind of makes sense as follows. A vector itself is a direction and a magnitude. Now, if you just divide out that magnitude, you're left with just a direction. And so the unit vector, the thing you get when you divide out by the magnitude, very naturally should be interpreted as a direction. Is that kind of plausible? Realistic sounding? Okay. All right. So again, use that unit vector, not the vector that's given, because again, that's what you have to do if you want to use these interpretations of a directional derivative. And everything else is arithmetic. Okay. Is everybody happy? All right. Now, one other little nasty little landmine that you got to worry about, and I've seen many a student step on this one. This is unfortunate. Let's talk about this language here where it says the direction of the vector, and again, we agreed that represents a unit vector. Okay, fine. But here is a different interpretation that students could make. Let's actually draw this out. Remember, we were looking at the point 1, 3. That's where we are. We're looking at this vector 3, 4, telling us which direction we're going. Wait a second. Now, we understand that it is the unit vector that represents the direction itself is when you divide by 5, that gets you this little shorter light blue vector. Okay, fine. Here's the landmine. Here's what a lot of students mess up on. A lot of students misinterpret the phrase direction of the vector as toward the point defined by that vector. Right? Now, if you were to interpret this 3, 4 as being a point, the point 3, 4 is, well, let's see here. There's 3, 4. Well, let's see. I didn't draw that well, but 3, 4 would be something kind of like this. There's the point 3, 4. And now the direction, the unit vector toward 3, 4, students would think sometimes perhaps of this red vector. And very importantly, that's not what this says. A vector is a direction and a magnitude. When we say the direction of the vector, we mean the direction, ignoring the magnitude, right? So direction is part of what a vector is. It just doesn't say toward the point 3, 4. Right? Does everybody see the distinction? Right? So you're going to get a really, really wrong answer if you mistakenly wrong color. If you mistakenly interpret this as being 3, 4, the point 3, 4, that's wrong. Then you will get the wrong direction there. Okay, so please be careful about that. And we move along now to the next example. The next example is really, really similar. A little bit different, not much. Here, now we're not looking at a graph. Here we are looking at temperature as a function of location. So again, one of my favorite examples, such as in this room, right? Temperature depends on where you are. Written in coordinates because, well, again, I confess coordinates are really convenient, and I'm not anti-coordinates, right? But that's written that way just so that we can. And the question here says, okay, how fast is my temperature increasing per unit distance traveled if I'm going in the direction of this vector 2, 4, 3? So I'm at a certain spot and I'm moving in a certain direction, and for every foot that I go in that direction, how much does the temperature change? Everybody okay with what the question's asking here? Yeah, okay. Okay, well, not a slope of a graph, but DTDS is one of our primary interpretations of the directional derivative. So I'm going to get my answer to this question by computing directional derivatives. Here's my handy formula for how to compute directional derivatives. And again, it's all downhill from here. You do have to be a little careful to recall that the vector that's given is not the unit vector, right? The unit vector representing the direction, I have to divide the given vector by its own magnitude. Right? So don't forget to unitize. Right? And everything else is basically algebra and arithmetic. Yes, you have to compute the gradient. Yes, you have to plug in the point in question. A little subsequent arithmetic. I'm going to let y'all read through those details. But the big ideas we've hit already. What do you think? Everybody all right? Okay. All right. Now, here is an unfortunate cultural point of this, and this is uncomfortable, but it is what it is. Some people like to define the idea of a directional derivative without the unit vector requirement. Now, that was a big deal for how we defined it. Right? What we have here is critical that this be a unit vector, because the point of view we're taking on this here is that this unit vector, it could have been a standard basis vector. No reason it couldn't have been. Let's pretend that it was. All these facts should still be true, independent of what arbitrary coordinate system we've used. Okay, so we hit that a lot. But if we allow V to be not a unit vector, then all of that business about it could have been a standard base, no, it can't. Everything's just going to change, and our point of view goes out the window. So here's the thing: if you remove this requirement, you lose this interpretation about it being a multiplicative factor, or DFDS. That's gone. You lose this interpretation about it being the slope of a graph. Gone. It just doesn't work. All the rest of this is good, though. So even without the unit vector requirement, some people still use the term directional derivative. It does create a confusion because, wait a second, do you mean in this sense or do you mean in the other sense? And that's unfortunate. But you can use the term. They use this notation. This is the definition. And really nicely, this formula here still works just fine. No problem. So this leftover, all of this working together, still pretty handy. And let me point out, even if I can't interpret it like this down here, this is still a natural object. This says, hey, I'm at the point A. I'm moving with a velocity, not necessarily unit vector velocity, but whatever. I'm at the point A. I'm moving with some velocity. And I want to know how fast the function's changing. How do I do that? Pretty natural. In fact, I would point out it's arguably more natural. Because let's face it, most of the time that I'm at some point A and moving, most of the time my velocity, in fact, in real life, probably not a unit vector. What are the odds? Right? So it's really a very natural thing to want to talk about. And this idea of just abandon this unit vector requirement allows me to talk about this thing. And gives me a nice notation and terminology for talking about this thing. Okay, now, two things to say about this. First thing is in this course, in Math219, we have to choose, right, which one to do. And I think the only reasonable answer on something like this is to go with the book's convention, right? So our Colley is our textbook, and we're going to go with Colley's choice on this. So Colley's definition does require that the vector be a unit vector, and as such, we get all of this together. right? You do have to use unit vectors. That's the price, right? But at the slight cost of this only applying to unit vectors, notation, definition, formula, and interpretations, all good. Okay, that's for Math219. Now, the second thing I want to say about this is that the time will come when you are no longer taking Math219. You'll be out and, taking engineering classes or whatever, physics classes maybe, and depending on who you're talking to, there may be a misunderstanding based on the fact that, again, some people do, some people don't with the whole unit vector thing. So what you have to do, and I don't know any other way around this other than to put the responsibility on y'all in your futures to just be heads up on this point. Make sure to clarify if, some engineering professor uses the term directional derivative. Ooh, hey, wait a minute. Do you mean unit vector or do you not mean unit vector? Just want to clarify. I know that people go different ways on this. Be prepared as well for them to be surprised by this. I've been surprised at how many people are surprised at this fact that there is a misunderstanding. A lot of people are they learned it a certain way in college and they've never heard of the other point of view. So, like I say, heads up. And good luck keeping it straight outside of Math219. In Math219, unit vectors only. Okay, let me pause on that for questions. Anybody? Okay. Right, so moving along. Next thing, we're going to consider a very natural question. We're going to think about this scenario where we have a multivariable function, differentiable, so we can use nice theorems about how to compute things, right? Gradients make sense, etc. We're going to assume differentiability. We're going to suppose that we are at a particular point, A, in the domain, and we're going to entertain the following question where I get to choose among all unit vectors. In other words, all possible directions, whatever. I'm trying to make these look like unit vectors. All possible unit vectors. Each one of those unit vectors, of course, would give me a certain value of the directional derivative. And I would like to know which one maximizes that directional derivative. Each direction gives me a directional derivative. Sometimes the directional derivative is more, sometimes it's less. Which one of these makes it as big as possible? Now this, I claimed is a really, really natural question. My favorite sort of easily relatable example is, okay, here's me. I'm out in the woods. I'm cold. This is the function that describes temperature. I can walk any direction that I need to walk. I just need to know which direction should I walk to make my temperature that I'm experiencing increase as fast as possible. I want to walk toward the warmth. Does that make sense? Right? Pretty natural, pretty unsophisticated, right? Pretty everyday, kind of reasonable question. Of course, there's a million other examples where you might want to know something like this. So, for example, maybe this point represents where the small business that you're operating is set up. Maybe these axes don't represent physical location. Maybe they represent the parameters of how you're running your business, how many employees you have, and how much money you borrowed from the bank, whatever. And maybe the function represents profit, and you pretty natural question. Hey, how should I start moving things? Should I be hiring more people and paying back the bank, or should I be borrowing more money and doing some layoffs? What do I have to do here to make profit go up as fast as possible? Or whatever, right? How do I keep risk as low as possible? Whatever, right? Millions of applications. Okay. Now, before I show you how to answer this question, I want to talk about terminology a little bit. this question. There's a couple of different terms you can use here. Keeping in mind that directional derivatives are interpreted in these two different ways. Right? You can think of it as a rate of change with respect to distance, how fast the function's increasing, that is. Or you can think of it as slope of the graph. Fine, either way, not a problem, all good. Well, the answer that we're going to end up finding, and arbitrarily, let's just suppose it's this one here, that vector is going to represent the direction that accomplishes a certain goal. And, well, if you think about the directional derivative as representing the rate of change of the function, and if we have found the vector that makes that rate of change of the function as great as possible, let me say that differently, we've then found the direction that makes the function increase as fast as possible. Wouldn't it make sense to call this the direction of fastest increase, based on that interpretation of the directional derivative that we've maximized? Now, alternatively, also perfectly reasonable, maybe we're looking at a graph. Not here, by the way. Right? Point that out. I'm not drawing a graph here. Sometimes I don't want to draw a graph. Sometimes I can't draw a graph. But hypothetically, if you were drawing a graph, and if you were thinking of the directional derivative as telling you the slope, and if you found the direction that makes your slope as great as possible, that's telling you then which direction goes uphill. Or said differently, which direction has you, as you go in that direction, which would have you climbing the mountain as fast as possible, which would have you ascending as steeply as possible. So you could call it the direction of steepest ascent. So these two different choices, just to describe this whichever vector it ends up being, direction of fastest increase, direction of steepest ascent. You can use either one of these terms. I'm partial to the first one myself because it makes sense in any context. The second one only really makes sense semantically if you're looking at a graph. And again, sometimes I'm not, sometimes I don't want to, sometimes I can't. Right? So I personally, I'm a fastest increase kind of guy. But for whatever it's worth, the rest of the world more so prefer the term steepest ascent. Again, I think that's unfortunate, but that is what it is. So be prepared. In my class, you're going to hear me say this, and once you leave this class, you're going to hear this. Okay. Does that make sense to everybody? Are we all good? Okay. All right. So let's answer the question then. How do we find this direction that makes our directional derivative as high as possible? Okay. There's our directional derivative. Want to make that as big as possible. Here's how we compute directional derivatives. Handy formula that we ripped off from partial derivatives. How do we compute dot products? Well, with this handy formula right here. Oh, now wait a minute. V has to be a unit vector, previously discussed. So that factor right there is just 1. The magnitude of a unit vector is always 1. So that goes away. So, okay, altogether then this is what we want to maximize. Now, wait a second. We can actually simplify this even further. Because while, yes, indeed, this is what we want to maximize, notice that the magnitude of the gradient is a constant. Now, why is that? Why is the magnitude of the gradient constant? The point is, because I haven't started moving yet. I'm at this point A. I am contemplating possible directions that I might move, right? But I haven't actually started moving yet. I am at this point, and the gradient is a function of where I am. It's a function of that point that isn't moving. So as I entertain all these different directions, the gradient doesn't change. And so, yes, while technically what I have in orange is what I want to maximize, it's just as good if I maximize just that, just the cosine theta. As long as that's maximized, the directional derivative is maximized. And this is great news because it's super easy to maximize cosine. You maximize cosine when theta is 0. Nothing to it. Now let's look back at the picture. Keep in mind, we've got our gradient vector here. We've got our, let's see here, our direction vector v, unit vector representing the direction we're going to go. And what is theta? Theta is the angle between those. Now, if I want this angle between these two vectors to be 0, okay, well, that just means that I need for my vector to be the one that actually points in the direction of the gradient points. And better represented then by this picture where my vector v is like that. And again, the angle between these two vectors then is 0. Does that make sense to everybody? Okay, so summarizing, we need to know what is the direction of fastest increase, what is the unit vector that points in the direction that the function's increasing the fastest. Okay, answer, the direction that the gradient points. Simple as that. Just compute the gradient, turn it into a unit vector, done. Nice simple punchline. Okay. All right, now natural next question. So we've agreed which direction we're going to go. We're going to go in this direction. Okay, fine. As I'm going in that direction, that's what maximizes the directional derivative. Okay, cool. How big is that directional derivative? Now, saying that in different terms, keeping in mind that the directional derivative on the one hand tells you how fast the function is increasing. So, as I go in this direction, how fast will I be getting warmer? Right? How fast will my profits be increasing in my small business? Whatever. Right? Also, sort of the different point of view that you can take here, thinking of the directional derivative as telling you the slope of the graph. Okay, fine. As I'm looking in this direction, how steep is the graph in that direction? And by the way, that's actually a really, really natural thing to want to know. If you're hiking, right? Here I stand on the side of this hill, and it's got a certain steepness in that direction. It's got a certain steepness in that direction. Might be really steep in that direction, but as I go this way, I'm basically just kind of following a contour line. But when people ask, how steep is the mountain? They mean, how steep is it uphill? Of course, right? So, again, really natural question. When they ask, how steep is the mountain, they mean in that optimal direction, where it is the steepest. That's the direction in which I want to know how steep it is. Okay, so again, really natural question. The computation's pretty straightforward. Let's see here. This is how we compute directional derivatives, keeping in mind that, as we just saw here, this vector is gradient divided by magnitude. Then notice that, let's see here, better color choices. Gradient dot gradient is gradient squared, magnitude squared. And so this whole thing together then just simplifies to the magnitude of the gradient. And what I think is lovely about this sequence of questions is that if you look at these two answers that we have here, right, that's the answer to our first question. What's the direction of fastest increase? This is the answer to our second question. How fast is it increasing? notice that both of these answers are gradient. This is the direction of the gradient. This is the magnitude of the gradient. The gradient is telling you both things. The gradient is simultaneously telling you what the best direction is and how fast it's increasing in that direction. Or said differently, it's pointing uphill, and the magnitude is telling you how steep the mountain is. Pretty neat. So that I summarize right here. I call this a geometric characterization of the gradient. So the gradient is telling you the direction of fastest increase and the rate of change, aka slope, however you want to call it, in that direction. Fine, cool, but notice what this is alternatively telling you is it's describing the gradient by way of the gradient's geometric characteristics. Right? We've previously understood gradient by its coordinates, its components. Gradient's made up of partial derivatives. Okay, algebraically that's handy. Computationally, right? Cool. But if you want a geometric sense for what gradient is, the geometric point of view on the gradient are that its direction and magnitude are understood in these senses. And the direction and the magnitude are its geometric features. How are we doing on that? Is that all right? Okay. Cool. Okay, so example. Now, before I get into the example itself, there's an awkwardness of language. It's annoying. Basically, I'm going to be describing here how I want to sweep a distinction under the rug, because what else could I have possibly meant? So here it is. Let's talk about this point, 1, 3, and let's see here. I guess I've drawn 1, 3. Not perfectly to scale, forgive me. But there's a point in the domain for this function. And now notice we're looking at a graph of that function, and you can recognize that graph as a upside down paraboloid, right? And so when I say that I'm at that point, well, really, that's where I actually am, right? So I might describe my location with longitude and latitude, right? That's how you describe, where is London? Well, it's, whatever longitude, whatever latitude. And it's also at an altitude, right? But nobody talks about that because you don't need to, because you're talking about something that you already know is on the surface. Then of course the altitude is whatever the altitude function says it is, right? So the awkward thing then is that while technically these are different points, right? This blue point is a point in the domain. This green point is a point on the graph. The blue point has 2 coordinates. The green point has 3 coordinates. They are different. That difference is important, but it's also unavoidably understood, and you have to know which one you mean and use the right one appropriately. Right? So I was careful when I phrased the question here. You'll notice that I described the point sitting above 1, 3. So I did distinguish blue from green in the phrasing of this question, but frankly, most of the time I won't, and frankly, also most of the time, most other people won't, right? So people will describe locations even though you're actually on the surface. People will describe the location with just the point in the domain. So, heads up, right? Make sure to be clear on this distinction, and make sure to always interpret appropriately. Interpret in the only way that could possibly make sense. You just got to be on the lookout for that. Okay, now with that noted, let's actually answer the question. So the question says, first of all, which way is uphill? We have an answer to that question. The direction of steepest ascent. Uphill is just a shorthand for in what direction is the altitude increasing the fastest. In other words, direction of steepest ascent. So the direction of steepest ascent, you get that by computing the gradient. Right? And at the point in question, the gradient is something like that, pointing in the sort of the negative x direction and the negative y direction from the point that we're sitting at. Easy to do. You just take the function, take the appropriate partials to get your gradient, plug in the point that you're actually sitting at. Boom. Everybody okay? I suppose, depending on how the question is phrased, arguably maybe I should, maybe I shouldn't have made this a unit vector, right? If the question had say, what is the direction, then technically, yeah, you should make this a unit vector. Depending on how it's phrased, it's not a big deal either way. Okay, next question. How steep is it? Well, again, how steep means what is the slope of that hill? The hill being the graph of that function. How steep means what is the slope of the graph. And the slope of the graph in the uphill direction is the magnitude of the gradient. That also super easy to compute. You just take the magnitude of the vector you just got through computing. 2 square root of 2. Pretty steep, right? That's 2.8 something. About like that. That's a steep hill. Everybody all right? Cool. All righty, moving along. Yeah, so level, see, how am I doing on time? Okay, so level sets. There's a surprising connection between gradients and level sets that comes by way of the idea of directional derivatives. I want to entertain the following scenario where I have a level set. It's a function of 3 variables, so the level set is a surface, again, described by when the function is a constant. And I consider the scenario where I am at a certain point, such as that point right there, A. Right, and now let's entertain what happens as from that point I start moving in the direction of a tangent vector. And what's going to happen? How fast does the function change if from this point on the level set I start moving in the direction of a tangent vector? And the clever idea here is to realize that if that's a tangent vector, then it is literally a velocity vector of a curve that is entirely within our surface. Right? So I've just drawn a curve here that's on our surface, and as this curve passes through this point, its velocity will be in the direction of, well, that tangent vector. Okay. So here's the thing. This curve that I've just drawn is entirely on my surface, where f is always c, which means that as I move along that curve, f is not changing at all. F is, says right here, f is constant. All right, so as I move along this curve, f is constant. Let me say that differently. As I move through this point and going in the direction that the curve is going, right? This blue vector is the velocity vector of this curve. As I'm at this purple point moving in this blue direction, the function's not changing. The rate of change of the function is 0. And that means that the directional derivative in this direction here, the directional derivative is 0. Is that cool so far? Cool. Works for any tangent vector. And it also tells me other things. If the directional derivative is 0, well, that means that the formula that I use to compute the directional derivative is 0, right? I compute directional derivatives as gradient dot v. So gradient dot v is 0. Oh, hey, wait a second. When a dot product is 0, that means that those two vectors are orthogonal and generically perpendicular. Right? So the nice punchline then is that the gradient vector, whatever the gradient vector is, it's got to be perpendicular to all the tangent vectors. And now I appeal to your geometric intuition. What vector is it that's perpendicular to all tangent vectors? There's really only one direction that's perpendicular to all the tangent vectors, and that's the direction perpendicular to the surface. So this is the shocking conclusion of this little analysis. Gradients are always perpendicular to level sets. Really cool fact. Gradients are always perpendicular to level sets. Specifically, be careful about this, the gradient of a function f is always perpendicular to the corresponding level set of that same function f. But, rolls off the tongue more nicely if you say gradients are always perpendicular to level sets. So, really nice fact. One last little quick comment. So, recall long ago when we first started talking about calculus, and I gave you all this warning that, heads up, the calculus of graphs is really, really different from the calculus of level sets, which is really, really different from the calculus of parametric curves. What we have here is an important fact about the calculus of level sets. Right? Gradients means calculus. This is in relation to level sets. Don't conflate this with the calculus of parametric curves. Remember, awkwardly, when you're looking at a parametric curve, the derivative, aka calculus, is a tangent vector because it's a velocity vector. So students used to get confused in my classes all the time. How come sometimes a derivative is perpendicular? How come sometimes it's parallel? What gives? You got to make sure to distinguish the kind of picture you're looking at. Are you looking at a level set? You're looking at a parametric curve, what have you. Y'all have a good day. See you later. Okay. Let's see here.